Okay, in this last video, we're going to talk about the final questions on the practice test. A stunt person jumps from the roof of a tall building, but no injury occurs because the person lands in a large air-filled bag. I'm sure we've seen this before. Which of the following best describes why no injury occurs? Well, ultimately, it comes down to impulse. If impulse is the change of momentum, and we have lots of momentum as the person is falling and no momentum when the person comes to a stop, well, the change in momentum ends up being exactly the same. We have the same momentum whether we fall into a bag filled of air or whether we land on the concrete. So that remains the same. What we can do, however, is increase the time that it takes to change our momentum. So if we increase time, then the force that's perceived by the person at impact must go down, because if the time increases, the force has to decrease in order for our impulse to stay the same. So by increasing the amount of time during which the momentum is changing, this reduces the average force on the person. In number 17, we know the mass of a tennis ball. The velocity initially of the tennis ball is 15 meters per second, and then after the impact, it's now 15 meters per second in the opposite direction. So let's go ahead and call the initial velocity a positive 15 and the final velocity a negative 15. During the impact, the ball remains in contact with the racket for 2/100ths of a second, or 20,000ths of a second. Our job is to find the magnitude of the force exerted on the ball. Well, we have lots of components here: mass, initial velocity, final velocity, and time. So if we recognize the change in momentum as the mass times velocity final minus mass times velocity initial, that change in momentum is equal to the force times the time of the impact, or the amount of time during the impact. So we'll divide both sides by t to isolate force, make our substitutions, and we see that the force exerted on the ball was 98 newtons. In number 18, we have a 1 kilogram ball, velocity of 12 meters per second downward. Now, depending on your frame of reference, you may call this one positive or negative. I'm going to call this one negative, since we usually label a downward direction as negative. After it bounces back up, it's proceeding with 12 meters per second velocity upward. So we'll go ahead and call that one a positive velocity. If we know the mass and the two velocities, can we determine the impulse delivered to the ball from the ground? Well, the impulse is the change in momentum. We already know the mass and the velocities, so simple substitution, we determine the impulse. Now, impulse is a vector, just like magnitude was a vector. So with impulse, the direction does matter. If we have a positive 24 and we indicated that a positive was an upward movement, then this result positive implies that we're moving upward. If we had switched our signs, if we had said that the positive direction was down and the negative direction therefore was up, then we would have expected to see a negative result here, but that still would have implied upward movement. So just be careful with your signs. Universally, I should say in general, we would say that downward movement is labeled as negative. However, from your point of reference, that may be different. So in any event, 24 kilogram meters per second. I forgot a component of my unit here. Kilogram meters per second, and we are moving upward. So I'll go with E as the result. Now, number 19 is simply a reference to the definition. A collision is elastic, and the definition of the elastic collision states that both momentum and kinetic energy are conserved. This is pretty difficult to do because there's often energy lost not lost, but transferred into heat due to friction and sound. So a perfectly elastic collision is very difficult to achieve. So in most real life scenarios, we would say almost perfectly elastic, or simply stated here, elastic would be just fine. If 100% of the kinetic energy is conserved and not transferred into another form of energy, then we would say that it is perfectly elastic. Now finally, we've got two cars that are traveling. One's due north and one is due east. If the collision is completely inelastic, that means these two will collide and stick together, right? So not just come to rest or anything, but they'll actually stick together upon collision. Well, hopefully you would recognize that the northward movement of car 1 and the eastward movement of car 2 would result in some sort of diagonal direction of the two. And so I think direction number 4 would be the best. Even though we don't know the masses of these objects or any of that additional information or their velocities or anything like that, I think it stands to reason that the objects would travel in some sort of diagonal direction this way. So I hope these series of videos help you out. As I had mentioned last week, I'd be willing to record a response to any questions that you have. At this point, I haven't gotten any requests for that, so that's why you're only seeing the 4 videos today. But if you've got any questions, I'll do my best to answer them. Just send them to me. And on Wednesday, I think I'll be down in the mechatronics lab fielding questions there. If any of you are in mechatronics and have questions, or if any of you are not in mechatronics and want to come down, that's where I'll be fielding questions. Thanks for watching.